Light carries no weight, yet it built every star in the universe. It has no substance, yet it powers every living thing on Earth. Tonight we'll gently explore this quiet paradox that sits at the heart of physics, how something that seems like pure nothingness can somehow be absolutely everything. We'll discover why a single photon weighs nothing but carries infinite possibility, why light exists everywhere and nowhere at once, and how this strange duality shapes reality itself from the smallest quantum dance to the vast cosmic web. It's a story of energy without mass, waves without water, and particles that aren't quite particles, unfolding slowly through the patient lens of science. If this gentle journey into one of nature's most beautiful mysteries helps you find peace or wonder, your soft like, your quiet subscription, and your thoughtful comments create a warm community of curious minds. Let's drift together into the luminous heart of this paradox. What if I told you that the light gently illuminating your space right now carries absolutely no weight, yet without it, nothing you see could exist? Welcome back to Science for Sleep, where we explore the beautiful mysteries that surround us with patience and wonder. I'm curious about your evening setup tonight. Perhaps you have a soft lamp casting warmth across your room, or maybe moonlight filtering through your window, or even just the subtle glow from your device screen. Each photon reaching your eyes represents one of nature's most elegant paradoxes. Particles that possess zero mass but carry infinite creative potential. If you find comfort in these gentle explorations of science, your quiet subscription and thoughtful engagement help build our contemplative community of curious minds. Tonight, we're embarking on a particularly fascinating journey into the heart of quantum mechanics, where logic bends and reality reveals its most counterintuitive truths. We'll move slowly through ideas that have puzzled brilliant scientists for over a century, allowing each concept to settle naturally before building upon it. The central enigma we're exploring asks how something that weighs nothing can be responsible for everything. How massless photons forge the bonds between atoms, power the nuclear furnaces of stars, carry information across cosmic distances, and literally create matter from pure energy. This isn't just academic curiosity, it's the foundation of existence itself. Every chemical reaction in your body depends on electromagnetic forces mediated by these weightless messengers. The warmth you feel, the colours you perceive, the very stability of matter around you emerges from interactions involving particles that exist at the boundary between being and nothingness. What makes this paradox even more beautiful is how it challenges our everyday understanding of substance and reality. In our familiar world, things that matter have mass, weight, presence. Yet photons operate by entirely different rules, existing only in motion, never at rest, carrying energy and momentum despite having no material substance. They are like cosmic ghosts that can push solar sails across the void, knock electrons from metal surfaces, and trigger the cascade of chemical reactions that enable vision. Scientists discovered this paradox gradually, through experiments that consistently defied explanation. Each new finding deepened the mystery rather than resolving it, revealing layers of strangeness that continue to inspire wonder today. The mathematics describing photons is breathtakingly elegant, yet the physical reality they represent seems almost magical. They emerge from quantum fields that permeate every cubic centimetre of space, spontaneously appearing and disappearing in dance with uncertainty itself. What's particularly remarkable about our photon paradox is how it bridges the smallest and largest scales of existence. The same quantum mechanical principles governing individual photons in laboratory experiments also explain how galaxies shine across billions of light years, how plants capture solar energy for life, and how information travels through fiber optic cables. This universality suggests something profound about the architecture of reality, that the cosmos operates on principles far stranger and more beautiful than our intuition suggests. As we drift deeper into this exploration, you might find yourself questioning fundamental assumptions about the nature of existence. That's perfectly natural when encountering quantum mechanics, where traditional logic often fails and new forms of reasoning emerge. Even Einstein struggled with these concepts, famously expressing discomfort with the probabilistic nature of quantum reality. Yet subsequent experiments have consistently confirmed the strange predictions of quantum theory, showing that nature truly does operate according to these counterintuitive rules. The beauty of tonight's journey lies not in reaching definitive answers, but in appreciating the profound questions that photons raise about the nature of reality itself. We'll explore how something without substance can have such enormous influence, how particles can exhibit wave-like behavior while waves demonstrate particle-like properties, and how the act of observation itself seems to influence quantum reality. These aren't merely abstract philosophical puzzles, but practical aspects of the universe that enable technologies from lasers to solar panels to quantum computers. So settle into comfort as we begin this gentle exploration of one of physics' most captivating mysteries. There's no pressure to understand everything immediately. Quantum mechanics rewards patience and contemplation over hasty comprehension. Let your curiosity guide you through concepts that continue to amaze scientists worldwide, and remember that confusion is often the first step toward deeper understanding. Have you ever wondered how sunlight streaming through your window can warm your skin when the particles carrying that warmth weigh absolutely nothing? Consider the illumination surrounding you at this very moment, whether it originates from your bedside lamp casting gentle shadows across familiar objects, the soft glow emanating from your phone screen as you listen, or perhaps starlight that travelled millions of years to reach your location tonight. Each luminous ray represents billions upon billions of photons, these extraordinary quantum entities that carry energy without possessing any mass whatsoever. The sensation of warmth touching your face when stepping into sunshine results from massless messengers delivering electromagnetic energy directly to your cells, triggering molecular vibrations that your nervous system interprets as heat. This everyday miracle happens countless times each second, yet we rarely pause to appreciate its fundamental impossibility according to classical physics. Those same weightless photons enable your vision by interacting with specialized proteins in your retinal cells, creating electrical tilt signals that your brain transforms into the rich tapestry of colors and shapes defining your visual experience. The lamp beside you operates on identical principles, with excited atoms in its filament releasing photons that illuminate your space through pure electromagnetic radiation. What makes this phenomenon even more remarkable is recognizing that every source of illumination around you demonstrates the same paradox at work. Your smartphone screen generates millions of photons per second, each one carrying specific wavelengths that create the precise colors displaying text and images. These particles possess momentum capable of exerting measurable pressure, yet they contain zero rest mass, existing only as pure energy in perpetual motion at light speed. The distant stars visible through your window represent perhaps the most awe-inspiring example of this paradox, operating on cosmic scales. Those massive stellar furnaces, some containing millions of times more matter than our entire solar system, sustain themselves through processes mediated entirely by massless photons. Nuclear fusion reactions deep within stellar cores release gamma rays that begin epic journeys lasting thousands of years, as they gradually work their way to the stellar surface, constantly interacting with matter through electromagnetic forces carried by particles without substance. The starlight eventually reaching your eyes tonight carries information about nuclear processes that occurred before human civilization existed, all transported by photons that somehow manage to traverse vast cosmic distances despite weighing nothing. This creates a fascinating paradox where the most massive objects in the universe depend completely on interactions involving massless particles for their very existence. Consider how photons enable the chemical processes sustaining life itself. Photosynthesis relies on plants capturing solar photons and converting their energy into chemical bonds that store power for biological systems. The glucose molecules fueling your metabolism right now originated from photons that struck plant leaves, demonstrating how massless particles literally become the substance of living matter through quantum mechanical processes. Your DNA contains carbon atoms forged in stellar cores through reactions mediated by electromagnetic radiation, meaning your physical being emerged from interactions involving massless photons across cosmic history. The wireless signals carrying information to your device operate through identical principles, with photons in radio frequency ranges transmitting data through electromagnetic waves that your technology converts back into meaningful information. These communication photons possess the same paradoxical nature as visible light, carrying energy and momentum while remaining utterly without mass, enabling instant information transfer across global distances. Even the warmth radiating from your own body represents infrared photons being continuously emitted by your cells as they maintain biological functions through electromagnetic processes. The gentle paradox extends beyond individual photons to encompass the electromagnetic field itself, an invisible ocean of potential energy pervading every location in space. This field gives rise to photons when disturbed, much like ocean waves emerging from underlying water. Yet the field itself represents something even more fundamental than the particles it produces. Quantum field theory suggests that what we perceive as empty space actually seethes with virtual photons constantly appearing and vanishing, creating a dynamic backdrop against which real photons operate. These virtual particles mediate forces between charged objects, meaning that electromagnetic interactions throughout the universe depend on exchanges of massless messengers that exist only temporarily before returning to the quantum vacuum. The implications stretch far beyond academic physics into practical applications that define modern civilization, from laser surgery to solar panels to fiber optic communications, all relying on manipulating massless particles to achieve tangible results in our material world. Why does embracing mystery often lead to deeper understanding than demanding immediate answers? Tonight's exploration into the photon paradox represents something quite different from traditional learning. We're embarking on a contemplative journey through concepts that have challenged humanity's greatest minds for generations. Rather than rushing toward conclusions, we'll gently discover how these massless particles accomplish their seemingly impossible feats, using comparisons drawn from your daily experiences to illuminate quantum mechanical principles. Think of this adventure as wandering through a vast intellectual landscape where each vista reveals new wonders, allowing curiosity to guide us naturally from one fascinating discovery to another. There exists profound beauty in acknowledging that complete comprehension isn't our goal. Instead, we seek appreciation for the elegant strangeness underlying physical reality. Quantum mechanics itself celebrates uncertainty as a fundamental feature rather than a temporary obstacle, teaching us that some aspects of nature remain inherently unpredictable, even with perfect knowledge of initial conditions. This perspective transforms confusion from frustration into invitation, encouraging us to sit comfortably with questions that may never receive final answers. Tonight's journey unfolds through carefully chosen analogies that connect abstract quantum concepts to familiar phenomena, much like using well-known landmarks to navigate unfamiliar territory. When we encounter photons exhibiting wave-particle duality, we'll compare this behavior to everyday experiences that demonstrate how single phenomena can manifest different characteristics depending on how we observe them. The electromagnetic field pervading space becomes as tangible as an invisible ocean supporting waves, while quantum fluctuations resemble the constant motion within apparently calm water. These comparisons aren't perfect replicas of quantum reality, but rather bridges helping our classical intuition approach genuinely counterintuitive truths. We'll discover how mathematical equations describing photon behavior achieve breathtaking elegance, while describing phenomena that seem almost magical in their impossibility. The relationship between energy, momentum, frequency, and wavelength creates a symphony of interconnected concepts, where changing one variable necessarily affects all others according to precise mathematical harmonies. Rather than overwhelming ourselves with complex calculations, we'll appreciate how these relationships enable photons to accomplish their cosmic roles as messengers, architects and creators throughout the universe. Each step forward builds upon previous insights while introducing new layers of complexity, allowing understanding to develop organically rather than through forced memorization. Consider how this exploration differs from examination or test preparation, where specific answers are expected within predetermined timeframes. Here, contemplation takes precedence over speed, reflection over recitation. The most profound insights often emerge during quiet moments between explanations, when abstract concepts suddenly connect with intuitive understanding through unexpected mental pathways. Some listeners may find certain ideas clicking immediately, while others percolate slowly, eventually blossoming into clarity during future reflections. This natural variation reflects how different minds process complex information, and there's no preferred timeline for developing quantum mechanical intuition. We'll encounter several seemingly contradictory statements about photon behavior that initially appear logically impossible yet prove absolutely accurate when examined through quantum mechanical principles. These apparent paradoxes aren't flaws in our understanding, but windows into a reality far stranger and more wonderful than classical physics suggested. Learning to hold contradictory concepts simultaneously without immediately resolving them develops mental flexibility essential for appreciating quantum phenomena. The journey ahead explores how measurements influence quantum systems, why observation changes reality at microscopic scales, and how particles can exist in multiple states simultaneously until specific interactions force them into definite configurations. These concepts challenge fundamental assumptions about objective reality while opening doors to technologies that seemed like science fiction just decades ago. Throughout our exploration, remember that even Nobel laureates continue discovering new aspects of quantum behavior, suggesting that mystery isn't a temporary gap in knowledge, but an intrinsic characteristic of nature itself. This perspective liberates us from feeling inadequate when encountering difficult concepts, instead encouraging wonder at participating in humanity's ongoing dialogue with the cosmos. We'll trace how photons emerge from quantum fields through creation operators, carry information across galactic distances, mediate forces between particles, and occasionally transform pure energy into matter through pair production processes. Each topic receives patient attention, with multiple approaches ensuring that various learning styles find pathways toward understanding. The mathematical beauty underlying these phenomena becomes accessible through geometric visualizations, musical analogies, and architectural metaphors that illuminate abstract relationships. As we progress, notice how interconnected these concepts prove to be, with each new insight enriching previous discoveries, rather than replacing them. This holistic approach mirrors how working scientists actually develop understanding, through accumulating perspectives that gradually coalesce into comprehensive worldviews. So settle into this gentle pace, allowing ideas to unfold naturally, without pressure for immediate mastery, trusting that comprehension develops best when given space to grow organically, through patient cultivation rather than forced acceleration. What happens when a single experiment shatters centuries of scientific certainty and forces humanity to reimagine the fundamental nature of reality itself? By the dawn of the 20th century, physicists had achieved remarkable confidence about electromagnetic radiation, viewing it as continuous waves rippling through space, much like undulations spreading across a pond's surface. Maxwell's elegant equations describe these phenomena with mathematical precision, explaining everything from radio transmissions to the colors of rainbows through wave mechanics that seemed unshakable in their theoretical foundation. Then Heinrich Hertz conducted what appeared to be a routine investigation into how ultraviolet illumination affected electrical sparks between metallic electrodes, unknowingly opening a door to quantum revolution that would transform our understanding of existence itself. The photoelectric effect, as this phenomenon became known, revealed behavior that classical wave theory simply could not explain, no matter how cleverly physicists attempted to reconcile their observations with established principles. When researchers shined light onto metal surfaces and measured the kinetic energy of ejected electrons, they discovered something profoundly disturbing. Increasing the brightness of illumination produced more electrons but failed to increase their individual energies, while changing the color of instant radiation dramatically altered electron velocities regardless of intensity. This observation violated every prediction of wave mechanics, which suggested that brighter light should deliver more energy per electron, just as larger ocean waves carry more power than smaller ones. The scientific community found itself confronting experimental results that demanded entirely new theoretical frameworks, challenging fundamental assumptions about electromagnetic radiation that had guided physics for generations. Into this conceptual crisis stepped Albert Einstein with a proposal so radical that even he initially doubted its implications. Perhaps electromagnetic radiation wasn't continuous waves after all, but rather discrete packets of energy that he called light quanta, later renamed photons by Gilbert Lewis. Einstein's revolutionary insights suggested that each quantum carried energy proportional to its frequency according to Planck's constant, meaning that blue light consisted of higher energy packets than red light, regardless of overall intensity. This concept resembled discovering that what appeared to be smooth ocean waves actually comprised countless individual water droplets, each carrying specific amounts of energy determined by the wave's characteristics rather than its amplitude. The photoelectric effect suddenly made perfect sense when viewed through this quantum lens. Electrons absorbed single photons in all-or-nothing interactions, gaining precisely the energy contained within each quantum, rather than accumulating power gradually from continuous waves. If photon energy fell below a threshold determined by the metal's properties, no electrons escaped regardless of how many low-energy quanta struck the surface, explaining why red light couldn't trigger photoelectric emission from certain materials no matter how intense the illumination became. Einstein's explanation required abandoning cherished concepts about electromagnetic continuity, replacing them with a granular picture of reality where energy transferred through discrete transactions between individual particles. This paradigm shift proved so unsettling that many prominent physicists, including Planck himself, initially rejected Einstein's quantum hypothesis despite its explanatory power. The scientific establishment had invested decades developing wave mechanics, creating mathematical tools and experimental techniques based on continuous field theories that suddenly seemed incomplete if not entirely incorrect. Robert Millikan, determined to disprove Einstein's radical claims, spent years conducting increasingly precise photoelectric measurements, only to confirm every prediction of quantum theory while reluctantly abandoning his classical prejudices. The resistance to accepting photons as real particles, rather than mathematical conveniences, reflected deeper philosophical struggles about the nature of physical reality itself. Einstein's quantum hypothesis implied that electromagnetic radiation exhibited dual characteristics, sometimes behaving like waves and other times like particles, depending on experimental circumstances. This duality challenged logical frameworks that demanded consistent behavior from physical entities, forcing scientists to embrace contradictory descriptions of identical phenomena. The implications extended far beyond academic debates, suggesting that reality itself might operate according to principles fundamentally different from human intuition about how things should work. Despite providing the theoretical foundation for countless technological advances from solar panels to digital cameras, Einstein's explanation of the photoelectric effect received surprisingly delayed recognition from the Nobel Committee, which awarded him the Physics Prize in 1921, 16 years after his groundbreaking paper appeared. This hesitation reflected ongoing skepticism about quantum mechanics among influential physicists who preferred classical explanations even when confronted with mounting experimental evidence supporting particle theories of light. The committee carefully avoided mentioning relativity in their citation, focusing instead on Einstein's quantum contributions that had achieved broader acceptance within the scientific community. Could a single particle somehow pass through two separate openings simultaneously, and then interfere with itself to create patterns that classical logic declares impossible? Thomas Young's ingenious double-slit experiment in 1801 seemed to settle forever the question of whether electromagnetic radiation consisted of waves or particles by demonstrating interference phenomena that only wave mechanics could explain. When Young allowed sunlight to pass through two closely spaced narrow slits cut into an opaque barrier, the resulting pattern projected onto a distant screen showed alternating bright and dark bands rather than simply two illuminated strips corresponding to each opening. This interference pattern proved that illumination from both slits was combining in complex ways with waves from different sources, either reinforcing each other to create brightness or cancelling completely to produce darkness where light plus light mysteriously equaled shadow. The mathematical description of this phenomenon required treating electromagnetic radiation as continuous oscillations that could superpose constructively or destructively depending on their relative phases, just like ripples spreading across water when multiple stones disturb a calm pond surface. Young's experimental results provided compelling evidence for wave theories of optics, demonstrating that coherent illumination could exhibit properties completely inconsistent with particle models where discrete entities should simply accumulate to produce uniform brightness proportional to the number arriving at each location. For over a century, interference experiments like Young's convinced physicists that electromagnetic radiation possessed fundamentally wave-like characteristics, supporting Maxwell's field equations and leading to tremendous technological advances based on manipulating coherent illumination through optical devices. However, the emergence of quantum mechanics during the early 20th century created an unprecedented puzzle when scientists developed technology capable of detecting individual photons and repeating Young's experiment with single particles rather than intense beams. These modern versions revealed something so counterintuitive that it challenged basic assumptions about physical reality. Even when photons passed through the apparatus one at a time, with significant delays between successive particles ensuring no possibility of mutual interaction, the same interference pattern gradually emerged as thousands of individual detections accumulated on the recording screen. Each photon seemed to interfere with itself, somehow travelling through both slits simultaneously despite being an indivisible quantum of electromagnetic energy that should follow, a definite path through one opening or the other, but never both. This phenomenon defied classical reasoning as thoroughly as discovering that a single raindrop could create concentric ripples on opposite sides of a pond without dividing into separate portions, suggesting that individual particles possessed properties transcending ordinary spatial limitations. The implications proved even more disturbing when researchers attempted to determine which slit each photon actually traversed by placing detectors near the openings to monitor particle trajectories. Whenever such measurements occurred, the interference pattern vanished completely, replaced by two simple bright bands corresponding exactly to classical expectations for particles following definite paths through individual slits. The mere act of observation fundamentally altered photon behavior, transforming wave-like entities capable of self-interference into particle-like objects with well-defined locations and trajectories. This measurement problem revealed that quantum systems don't possess definite properties independent of experimental arrangements designed to observe them, challenging philosophical assumptions about objective reality existing independently of conscious observation. The transition between wave-like and particle-like behavior occurred instantaneously upon measurement, suggesting that photons existed in quantum superposition states encompassing all possible paths simultaneously until specific interactions forced them into definite configurations. Researchers discovered that even partial information about photon trajectories degraded interference patterns proportionally, indicating that the degree of wave-like behavior correlated inversely with the precision of position measurements according to fundamental uncertainty principles governing quantum mechanics. These findings implied that electromagnetic radiation exhibited complementary aspects that could never be observed simultaneously, requiring physicists to abandon hopes of developing complete classical descriptions of quantum phenomena. The double-slit mystery deepened further when scientists realized that interference patterns depended not only on whether measurements occurred, but also on what information such measurements could theoretically provide, even if nobody actually recorded or analyzed the results. Quantum systems seem to respond to the mere possibility of observation rather than its actual occurrence, suggesting that information itself played a fundamental role in determining physical outcomes. Modern variations of Young's experiment continue revealing new aspects of quantum mechanical complementarity, with each technological advance enabling more precise control over photon detection while consistently confirming the impossibility of simultaneously observing wave and particle characteristics of individual electromagnetic quanta. What if the very concept of asking whether something is a wave or a particle reveals the limitations of human language rather than describing fundamental reality? Photons represent quantum entities that transcend classical categorization, existing as something far more sophisticated than either traditional waves or conventional particles could ever be. These electromagnetic quanta embody a completely novel form of existence that our everyday vocabulary struggles to capture, forcing us to acknowledge that nature operates according to principles fundamentally different from our intuitive expectations about how objects should behave. The dual nature of photons doesn't mean they alternate between being waves and particles like actors switching costumes, but rather suggests that these familiar concepts represent incomplete glimpses of a deeper quantum reality that encompasses both descriptions while transcending each individual perspective. When we design experiments to detect wave properties, photons obligingly demonstrate interference, diffraction, and frequency-dependent behaviors that perfectly match our mathematical models of electromagnetic oscillations. Conversely, when experimental apparatus is configured to reveal particle characteristics, those same photons exhibit localized interactions, discrete energy transfers, and momentum exchanges consistent with point-like entities carrying specific quantities of energy and momentum. This remarkable adaptability indicates that photons themselves remain constant while our experimental choices determine which aspects of their quantum nature become accessible to measurement and observation. The observation effect represents one of quantum mechanics' most profound insights. Physical reality at microscopic scales depends fundamentally on how we choose to examine it, suggesting that the act of measurement participates actively in creating the phenomena we detect as, rather than simply revealing pre-existing properties. This participatory universe concept challenges deeply held beliefs about objective reality existing independently of conscious observers, implying instead that the boundary between observer and observed becomes meaningless at quantum scales where measurement inevitably disturbs the system being studied. Niels Bohr formalized this insight through his principle of complementarity, which recognizes that complete understanding of quantum systems requires multiple, seemingly contradictory descriptions that cannot be unified into single classical pictures but together provide comprehensive knowledge about quantum behavior. Different experimental setups reveal different facets of photon reality, much like examining a river from various perspectives yields distinct but equally valid insights into its nature. Observing flowing water from above reveals patterns of current, turbulence, and overall movement that emphasize fluid continuity and wave-like propagation of disturbances across the surface. However, diving beneath the surface and examining the same river at molecular scales exposes discrete H2O molecules with specific positions, velocities, and individual interactions that create the macroscopic flow through countless microscopic collisions and exchanges. Neither perspective provides complete information about river behavior, yet both contribute essential elements to comprehensive understanding of aquatic phenomena. Similarly, wave descriptions of photons capture their ability to propagate through space, exhibit interference effects, and carry electromagnetic field oscillations across cosmic distances, while particle descriptions explain their localized interactions, discrete energy quantization, and ability to trigger specific responses in detectors and biological systems. Quantum mechanics teaches us to embrace this fundamental uncertainty as a feature rather than a flaw in our understanding, recognizing that nature itself exhibits inherent indeterminacy that no amount of technological sophistication can eliminate. The Heisenberg uncertainty principle mathematically formalizes this concept, demonstrating that certain pairs of properties cannot be simultaneously measured with arbitrary precision, not due to experimental limitations but because of fundamental constraints built into the fabric of reality itself. This principle applies directly to photons, whose position and momentum cannot both be determined exactly, reflecting the deeper truth that quantum entities don't possess definite values for all properties simultaneously, but exist in superposition states that encompass multiple possibilities until specific interactions collapse them into measured outcomes. The comfort we can find in this uncertainty stems from recognizing that mystery represents an authentic characteristic of existence rather than a temporary gap in human knowledge awaiting future resolution. Quantum mechanics has matured into the most successful theory in physics history, enabling unprecedented technological achievements while simultaneously revealing that complete classical understanding of microscopic phenomena remains forever beyond reach. This limitation doesn't represent failure, but instead opens doorways to appreciating the genuine strangeness and beauty of a universe far more subtle and sophisticated than early scientific pioneers could have imagined. Photons exemplify this quantum personality perfectly, serving as ambassadors from a realm where classical intuition fails but mathematical beauty and experimental precision converge to reveal nature's deepest secrets. They invite us to expand our conceptual frameworks beyond rigid either-or thinking toward more flexible both-and perspectives that accommodate paradox as a pathway to deeper truth rather than an obstacle to understanding. How can mathematical equations describe the properties of entities that possess zero substance yet carry measurable energy and momentum through the vacuum of space? The concept of zero rest mass represents one of physics' most elegant paradoxes, where photons exist as massless messengers that nonetheless transport finite quantities of energy and momentum across cosmic distances at exactly the speed of light. Understanding what zero rest mass actually means requires abandoning intuitive notions about matter and embracing relativistic principles that govern high-speed phenomena throughout the universe. In Einstein's special relativity, the familiar equation E=mc² transforms dramatically for massless particles, becoming E=p/c, where p represents momentum and c denotes light's velocity in vacuum. This mathematical transformation reveals profound implications about photon behavior that distinguish these quantum entities from all massive particles in fundamental ways, Whereas objects with mass can theoretically be brought to rest in some reference frame, photons cannot exist in stationary states because their very existence depends upon perpetual motion at light speed. They resemble bicycles that must maintain forward momentum to remain upright and functional. Except photons face an even more extreme constraint where stopping would mean ceasing to exist entirely rather than simply falling over. The relationship between photon energy and momentum follows directly from relativistic mechanics, where the general energy momentum equation E squared equals m squared, c to the fourth plus p squared, c squared reduces to E equals pc, when rest mass m equals 0. This mathematical simplification contains breathtaking physical consequences, establishing that photon energy depends entirely on momentum and frequency rather than any intrinsic mass properties. Higher frequency photons carry more energy per particle, explaining why ultraviolet radiation can damage biological tissues while visible light produces no harmful effects, despite both consisting of massless electromagnetic quanta. The speed of light emerges naturally from this mathematical framework as the only possible velocity for massless particles, creating a universe where certain entities must travel at this fundamental speed limit while others cannot possibly reach it. Massive particles require infinite energy to approach light speed because their relativistic mass increases without bulb bound as velocity approaches c, making acceleration beyond this threshold physically impossible regardless of applied forces. Conversely, photons cannot travel slower than light speed because reducing their velocity would require possessing rest mass, contradicting their fundamental massless nature and rendering them different types of particles entirely. This creates a cosmic speed limit that divides all particles into two distinct categories based on whether they possess rest mass or exist as pure energy in motion. The mathematical elegance describing photon properties extends beyond simple energy-momentum relationships to encompass complex quantum mechanical behaviors involving wave-particle duality, superposition states, and probabilistic interactions with matter. Photon wave functions satisfy relativistic wave equations that predict interference patterns, diffraction phenomena, and polarization effects observable in countless experiments from laboratory interferometry to astronomical observations of distant galaxies. These mathematical descriptions achieve remarkable precision in predicting experimental outcomes while simultaneously revealing the inherent limitations of classical thinking about particle behavior at quantum scales. Quantum field theory provides even deeper mathematical frameworks for understanding photon properties, treating these particles as excitations of the underlying electromagnetic field that permeates all spacetime. Creation and annihilation operators in this formalism describe how photons spontaneously emerge from and disappear back into the quantum vacuum through processes that conserve energy and momentum while allowing temporary violations of these. Conservation laws according to Heisenberg uncertainty principles. The mathematics becomes increasingly abstract yet maintains direct connections to measurable phenomena, demonstrating how sophisticated theoretical frameworks can accurately describe reality despite transcending everyday experience and intuition. Virtual photons represent another mathematical concept with profound physical implications, mediating electromagnetic forces between charged particles through exchanges that occur below the threshold of direct detection, yet produce observable effects on particle trajectories and interaction cross-sections. These virtual exchanges follow the same mathematical rules as real photons, but exist for times too brief to satisfy energy conservation requirements exactly, illustrating how quantum mechanics permits temporary borrowing of energy from the vacuum, provided the debt gets repaid within time intervals determined by uncertainty relations. The mathematical beauty underlying photon, physics reflects deeper symmetries in nature's fundamental laws, where gauge-eddy invariance requires electromagnetic interactions to be mediated by massless particles with specific spin properties. These symmetry principles constrain possible forms of physical laws, while enabling remarkably precise predictions about photon behavior in diverse circumstances, from atomic transitions to cosmological phenomena involving electromagnetic radiation propagating across billions of light-years through expanding space-time. What if the particles we observe represent merely temporary disturbances in invisible oceans of energy that completely fill every cubic millimeter of seemingly empty space? Quantum field theory revolutionizes our understanding by proposing that electromagnetic fields constitute the fundamental fabric of reality. while photons emerge as localized excitations rippling through this omnipresent substrate like waves, arising from an infinite cosmic ocean. This perspective transforms our conception of nothingness itself, revealing that vacuum contains seething activity where virtual particle pairs constantly appear and vanish according to uncertainty principle, constraints that permit temporary energy fluctuations provided they resolve within quantum mechanical time limits. The electromagnetic field extends throughout all regions of spacetime, creating an invisible matrix that supports photon propagation while simultaneously mediating forces between charged objects through virtual particle exchanges occurring below direct detection thresholds. Unlike classical fields that simply describe forces acting between separated objects, quantum fields possess intrinsic dynamical properties enabling them to spawn real particles when sufficient energy becomes available through external sources or spontaneous quantum fluctuations. Creation operators in quantum field theory mathematics describe precisely how photons emerge from the underlying field through processes that increment particle number while conserving energy, momentum, angular momentum, and other fundamental quantities according to established physical laws. These operators act on quantum field states to produce new particles with specific frequencies, polarizations, and momenta, functioning like mathematical instructions for extracting discrete quanta from the continuous field background. Annihilation operators perform the reverse transformation, causing existing photons to dissolve back into the field from which they originated, thereby decreasing particle number while returning their energy to the underlying vacuum state. The interplay between creation and annihilation processes maintains dynamic equilibrium within quantum fields, where particles continuously emerge and disappear according to probabilistic rules that produce stable statistical distributions over macroscopic time intervals. This constant turnover resembles oceanic activity where individual waves form, propagate, and dissipate, while the underlying water remains present throughout all transformations, providing substrate for endless cycles of disturbance and restoration. Virtual particles represent perhaps the most mind-bending consequence of quantum field theory, existing as temporary fluctuations that violate energy conservation for brief periods permitted by Heisenberg uncertainty relations governing quantum mechanical systems. These ephemeral entities mediate electromagnetic interactions between charged particles through momentum transfer processes that produce measurable forces despite involving particles that exist too briefly to be directly detected through conventional measurement techniques. Virtual photon exchanges create attractive forces between opposite charges and repulsive interactions between similar charges, establishing the electromagnetic phenomena that bind atoms together and enable all chemical reactions throughout the universe. The mathematical formalism describing virtual particle interactions achieves extraordinary precision in predicting experimental outcomes, including subtle effects like the anomalous magnetic moment of electrons and Lamb shifts in atomic energy levels that arise from vacuum fluctuations affecting particle behavior at quantum scales. Quantum electrodynamics calculations involving virtual photons yield theoretical predictions matching experimental measurements to more than 10 decimal places, representing the most accurate theoretical framework ever developed in science history. The quantum vacuum itself emerges as a dynamic entity teeming with activity rather than empty nothingness, containing zero-point energy fluctuations that persist even at absolute zero temperature, where all thermal motion ceases. These vacuum fluctuations produce observable effects including the Casimir force between closely spaced conducting plates, spontaneous emission of photons by excited atoms, and modifications of particle masses through self-energy corrections, involving virtual particle loops. Vacuum polarization phenomena demonstrate how empty space responds to external electromagnetic fields by producing virtual electron-positron pairs that partially screen the original field, creating subtle but measurable changes in interaction strengths that depend on energy scales involved in specific processes. The field concept extends beyond electromagnetism to encompass all fundamental forces in nature, with each interaction type possessing its own quantum field that fills space-time and supports particle excitations with characteristic properties determined by underlying symmetries and conservation laws. Quantum chromodynamics describes strong nuclear forces through gluon fields that confine quarks within protons and neutrons, while electroweak theory unifies electromagnetic and weak interactions through gauge fields that spontaneously break symmetry to produce massive W, N, and Z bosons alongside massless photons. Quantum field theory provides the theoretical framework underlying the standard model of particle physics, successfully describing all known fundamental interactions except gravity while predicting the existence of new particles subsequently discovered through high-energy accelerator experiments. The field perspective suggests that apparent emptiness conceals incredible complexity, with spacetime itself serving as substrate for dynamic processes that generate the entire menagerie of particles and forces observable throughout the cosmos. Why does nature seem to dance away from our attempts to pin down its fundamental properties with absolute precision, as if reality itself enjoys maintaining an element of mystery? The Heisenberg uncertainty principle reveals one of quantum mechanics' most profound truths. Certain complementary properties of particles can never be measured simultaneously with perfect accuracy, not due to technological limitations, but because of intrinsic constraints woven into the fabric of existence itself. For photons, this principle manifests as an inverse relationship between position and momentum determination, where increased precision in locating a particle necessarily decreases our ability to specify its velocity or direction with equal exactness. This fundamental limitation emerges directly from the wave nature of matter and radiation, reflecting the mathematical impossibility of defining both wavelength and spatial localization for the same quantum entity without inherent trade-offs between these complementary descriptions. The act of measuring photon position requires confining the particle to specific spatial regions, which inevitably involves interactions with detection apparatus that disturb the quantum system being observed and alter its momentum in unpredictable ways. Conversely, determining photon momentum precisely demands observing wave properties over extended spatial distances, necessarily sacrificing information about exact location in favor of frequency and directional measurements that characterize the particle's motion through space. This quantum mechanical trade-off creates a cosmic speed limit for information gathering, establishing that complete knowledge of all particle properties remains forever beyond experimental reach regardless of technological sophistication or measurement ingenuity. Wave-particle duality emerges as a direct manifestation of uncertainty relations, where the degree of wave-like behavior exhibited by photons correlates inversely with the precision of position measurements performed on an individual quanta. When experiments are designed to localize photons very precisely, their wave characteristics become suppressed and particle-like properties dominate the observable phenomena. While measurements that preserve wave coherence necessarily sacrifice detailed position information to maintain interference capabilities, this dynamic relationship between complementary aspects of photon behavior reflects deeper principles, governing all quantum mechanical systems, where the choice of experimental configuration fundamentally determines which properties become accessible to observation and which remain hidden behind uncertainty veils. The observer effect in quantum mechanics represents active participation rather than passive detection, transforming measurement from neutral information gathering into creative interaction that partially determines the reality being observed through unavoidable disturbances introduced by detection processes. Attempting to observe quantum phenomena resembles trying to photograph a flowing river using camera flashes that disrupt the water's motion, where each illumination pulse necessary for image capture simultaneously alters the flow patterns being documented. The resulting photographs capture real information about river behavior, but inevitably show modified conditions influenced by the measurement process itself, rather than purely natural undisturbed flow. Similarly, photon detection requires interactions between electromagnetic quanta and measurement devices that necessarily transfer energy and momentum, changing the quantum state being observed in ways that become incorporated into experimental results. This participatory aspect of quantum measurement challenges classical assumptions about objective reality existing independently of conscious observers, suggesting instead that the boundary between subject and object becomes meaningless at microscopic scales, where measurement and reality creation merge into unified processes. The mathematical formalism describing uncertainty relations achieves remarkable precision despite encoding fundamental limits on simultaneous knowledge acquisition, demonstrating how rigorous quantitative frameworks can illuminate the boundaries of possible understanding while maintaining predictive power for statistical measurements involving large numbers of particles. Heisenberg's uncertainty principle applies not only to, position and momentum, but extends to other complementary properties including energy and time, creating temporal limitations on how precisely brief quantum events can be characterized without violating conservation principles that govern all physical interactions. Virtual particle phenomena emerge directly from energy-time uncertainty relations, permitting temporary violations of energy conservation provided such borrowing from the quantum vacuum gets repaid within time intervals inversely proportional to the energy deficit involved in specific processes. These uncertainty-enabled fluctuations pervade empty space with constant activity, where particle-antiparticle pairs spontaneously appear and annihilate while mediating forces between distant objects through momentum exchanges that occur below direct detection thresholds. The philosophical implications of quantum uncertainty extend beyond technical physics into broader questions about the nature of knowledge itself, suggesting that complete deterministic descriptions of natural phenomena may represent impossible goals rather than temporary limitations awaiting future theoretical breakthroughs. Quantum mechanics teaches us to embrace probabilistic thinking as fundamental rather than approximate, recognizing that genuine randomness operates at the heart of physical processes rather than merely reflecting incomplete information about underlying deterministic mechanisms. This perspective transforms uncertainty from obstacle into insight, revealing that nature's reluctance to surrender all secrets simultaneously protects the creative potential inherent in quantum superposition, states that enable remarkable phenomena from laser operation to biological photosynthesis. Can pure energy spontaneously transform into solid matter, essentially creating something from nothing in a process that reverses Einstein's famous equation and demonstrates the universe's most fundamental creative mechanism? Pair production represents one of nature's most astounding phenomena, where high-energy photons undergo transformation into material particles, literally converting electromagnetic radiation into electron-positron pairs that possess definite mass, charge, and spin characteristics completely absent from their massless parent photon. This remarkable process operates according to Einstein's mass-energy equivalence relation running in reverse, where E=mc² becomes the blueprint for converting concentrated energy into substantial matter through quantum mechanical interactions that occur when gamma-ray photons interact with intense electromagnetic fields near atomic nuclei. The threshold energy requirement for pair production reflects the rest mass energies of created particles, demanding photons carry at least 1.022 million electron volts to generate electron-positron pairs, with any excess energy appearing as kinetic motion in the newly created matter particles. This energy threshold establishes a cosmic barrier below which photons cannot directly create matter, explaining why visible light photons lack sufficient energy density to spontaneously generate material particles despite their ability to influence existing matter through vacuum photoelectric and Compton scattering processes. When photon energies exceed this critical threshold, the electromagnetic quantum approaches close enough to massive atomic nuclei that intense electric fields surrounding charged protons provide the necessary interactions and strength to catalyze matter creation through momentum and energy conservation processes that transform pure radiation into concrete particles with measurable physical properties. The cosmic significance of pair production extends far beyond laboratory demonstrations, representing the fundamental mechanism through which the early universe populated itself with matter following the Big Bang, when temperatures and energy densities reached levels sufficient to convert primordial electromagnetic radiation into the elementary particles that eventually assembled into atoms, stars, galaxies, and ultimately all complex structures observable throughout the cosmos today. High-energy astrophysical environments including supernova explosions, neutron star mergers, and black hole accretion disks continue creating matter through pair production process, demonstrating that this conversion mechanism operates continuously throughout cosmic evolution, rather than representing merely historical phenomena confined to universe's earliest moments. The analogy of invisible music notes becoming visible dancers captures the essence of this transformation beautifully, where insubstantial sound waves containing rhythm, melody, and harmonic structure inspire physical movements that embody musical information through material expression, while adding new dimensions of interpretation and creativity to the original composition. Similarly, massless photons carrying specific frequencies, polarizations, and energy densities can materialize into tangible electron-positron pairs that inherit electromagnetic properties from their parent radiation while acquiring additional characteristics including electric charge, magnetic dipole moments, and fermionic spin statistics that enable entirely new categories of physical interactions impossible for their photonic predecessor. The mathematical description of pair production involves complex quantum electrodynamics, calculations incorporating Feynman diagrams that map possible interaction pathways between incoming photons, virtual particles mediating nuclear forces, and outgoing matter-antimatter, pairs created through energy conversion processes that strictly conserve momentum, angular momentum, electric charge, and other fundamental quantities. These theoretical frameworks achieve extraordinary precision in predicting experimental cross-sections for pair production under various conditions, including dependencies on photons, energy, target nucleus properties, and electromagnetic field strengths that determine interaction probabilities and angular distributions of created particles. Virtual pair production represents an even more subtle manifestation of energy-matter conversion, where photons with insufficient energy to create real particle pairs can temporarily generate virtual electron-positron pairs that exist briefly within time intervals permitted by Heisenberg uncertainty relations before annihilating back into electromagnetic radiation. These virtual processes contribute measurably to photon propagation through vacuum, creating slight delays and polarization rotations that become detectable in precision experiments involving intense laser fields or astronomical observations of light traversing vast cosmic distances through regions containing strong magnetic fields. The reciprocal process of pair annihilation demonstrates the reversibility of energy-matter conversion, where electron-positron encounters result in complete mass conversion back into electromagnetic radiation, typically producing 2 or more gamma-ray photons that carry away the original particle rest masses plus any kinetic energies possessed before annihilation occurred. Positron emission tomography exploits this annihilation signature for medical imaging, using radioactive tracers that emit positrons, subsequently annihilating with tissue electrons to generate characteristic photon pairs detected by surrounding instruments that reconstruct three-dimensional images showing metabolic activity and blood flow patterns throughout living organisms. The broader implications of photon-mediated matter creation extend into cosmological theories about universe origin and evolution, suggesting that all material existence ultimately derives from electromagnetic radiation through various direct and indirect pathways that converted primordial energy into increasingly complex atomic and molecular structures capable of supporting chemistry, biology, and consciousness itself. How can massive stellar furnaces weighing millions of times more than Earth sustain themselves for billions of years through processes entirely dependent on massless photons mediating electromagnetic interactions at their blazing cores? Nuclear fusion reactions powering stars throughout the universe rely fundamentally on electromagnetic forces that enable protons to overcome mutual repulsion and merge into heavier elements, with photons serving as both catalysts facilitating these reactions and primary products carrying released energy away from stellar interiors towards surrounding space. The proton-proton chain reaction converting hydrogen into helium within stellar cores generates gamma-ray photons possessing enormous energies that begin epic journeys lasting tens of thousands to hundreds of thousands of years as they gradually work their way from dense central regions through successive atmospheric layers towards stellar surfaces where they finally escape into interstellar space. During this prolonged migration, high-energy gamma rays undergo countless absorption and re-emission events as they interact with stellar plasma, progressively losing energy through each encounter until they emerge as visible light photons carrying specific spectral signatures that encode information about nuclear processes, elemental abundances, magnetic field strengths, and physical conditions existing within stellar interiors. These escaping photons become cosmic messengers broadcasting detailed information about stellar composition, age, temperature, rotation rates, and evolutionary status to astronomers throughout the galaxy, who decode their electromagnetic signals using spectroscopic techniques that reveal atomic fingerprints embedded within starlight wavelengths. The carbon atoms comprising organic molecules in your body originated within stellar cores through triple alpha processes, where electromagnetic forces enabled 3 helium nuclei to fuse into carbon through reactions mediated by photons that provided energy transport mechanisms necessary for sustaining nuclear burning at temperatures exceeding 100 million Kelvin. Silicon, oxygen, iron, and virtually every element to heavier than hydrogen and helium were forged within stellar furnaces through successive fusion reactions that required electromagnetic interactions to overcome nuclear repulsion barriers and enable element synthesis throughout cosmic evolution. Stars function as cosmic foundries where electromagnetic radiation serves simultaneously as manufacturing tool and finished product, with photons facilitating nuclear reactions that build heavier elements while also transporting synthesized materials throughout the universe via stellar winds and explosive supernovae that scatter processed matter across interstellar space for incorporation into future planetary systems. The electromagnetic spectrum emitted by stars spans from radio, waves generated in stellar coronae through visible light produced in photospheric regions, to X-rays originating from magnetic reconnection events, creating comprehensive electromagnetic portraits that reveal stellar physics operating across multiple energy scales and atmospheric layers. Photon pressure within stellar interiors provides crucial support against gravitational collapse, with electromagnetic radiation exerting outward forces that balance inward gravitational attraction throughout most of stellar lifetimes, until nuclear fuel depletion disrupts this delicate equilibrium and triggers dramatic evolutionary changes, including expansion into red giant phases or catastrophic supernova explosions. Stellar magnetic fields interact strongly with charged particles and electromagnetic radiation, creating complex plasma dynamics that produce sunspots, solar flares, coronal mass ejections, and other phenomena that demonstrate intimate connections between electromagnetic forces and stellar behavior observable through various wavelengths of emitted radiation. The opacity of stellar matter to electromagnetic radiation creates the prolonged photon diffusion timescales that characterize energy transport from nuclear burning cores to radiating surfaces, with photon mean free paths measuring only centimeters in dense stellar interiors, compared to the hundreds of thousands of kilometers separating core and photosphere regions. Stellar nucleosynthesis processes depend critically on electromagnetic cross-sections that determine reaction rates for various nuclear fusion pathways, with photodisintegration reactions competing against alpha particle capture processes to establish equilibrium abundances of synthesized elements under extreme temperature and pressure conditions existing within stellar cores. Variable stars demonstrate how electromagnetic emission patterns change over time as stellar structures pulsate, undergo mass loss, or experience thermal instabilities that modulate photon production rates and create periodic brightness variations detectable across vast cosmic distances. Binary star systems reveal electromagnetic interactions between stellar companions through phenomena, including mass transfer, accretion disk formation, and nova explosions where electromagnetic radiation mediates energy and angular momentum transport processes that govern binary evolution and ultimately determine final stellar remnant configurations. Stellar evolution theory predicts how electromagnetic properties change throughout stellar lifetimes as nuclear fuel consumption progresses and central temperatures evolve, with theoretical models achieving remarkable agreement with observational data when electromagnetic opacity calculations and photon transport mechanisms are properly incorporated into stellar structure equations. The cosmic recycling of stellar material through electromagnetic processes ensures that elements synthesized within stellar cores eventually become incorporated into interstellar clouds that collapse to form subsequent generations of stars and planetary systems, perpetuating cycles of cosmic evolution driven by electromagnetic interactions operating across multiple spatial and temporal scales throughout universe history. What if every photon streaming through space carries not just energy and momentum, but also serves as a fundamental information carrier that enables the universe to organize itself into increasingly complex structures from simple atoms to conscious beings? Electromagnetic radiation functions as nature's primary communication system, transmitting data about quantum states, molecular configurations, and energy distributions that guide the formation and maintenance of organized matter throughout cosmic evolution. Molecular bonds depend entirely on electromagnetic interactions where electrons sharing between atoms creates chemical structures through processes mediated by virtual photons exchanging momentum and angular momentum according to quantum mechanical selection rules that determine allowed molecular geometries and binding energies. These electromagnetic forces enable atomic nuclei to capture and arrange electrons in precise orbital configurations that minimize total system energy while satisfying Pauli exclusion principles, creating stable chemical elements capable of forming countless molecular combinations through shared electromagnetic fields that communicate bonding information between participating atoms. DNA replication exemplifies how electromagnetic interactions guide biological information processing, with hydrogen bonds between complementary base pairs formed through dipole-dipole electromagnetic attractions that ensure accurate template copying during cellular reproduction processes. The double helix structure itself results from electromagnetic forces balancing attraction between paired bases against repulsion between negatively charged phosphate groups along the DNA backbone, creating optimal geometric arrangements that protect genetic information while enabling access for transcription and replication machinery. Photosynthesis represents perhaps the most remarkable example of electromagnetic information processing in biological systems, where chlorophyll molecules capture solar photons and convert their energy into chemical bonds through electron transport chains that channel electromagnetic excitation energy through precisely organized protein complexes embedded within cellular membranes. The quantum efficiency of photosynthetic light harvesting approaches theoretical limits, suggesting that evolutionary processes have optimized electromagnetic energy capture mechanisms through billions of years of natural selection that favored organisms capable of extracting maximum useful work from available electromagnetic radiation. Light harvesting antenna complexes in photosynthetic organisms demonstrate sophisticated electromagnetic engineering where hundreds of chlorophyll molecules cooperate to funnel absorbed photon energy toward reaction centers through quantum coherence effects that maintain energy's transmission efficiency despite thermal fluctuations and molecular disorder present in warm biological environments. Enzyme catalysis involves electromagnetic field fluctuations that lower activation barriers for chemical reactions by creating favorable electrostatic environments around transition state configurations, enabling biological systems to accelerate reaction rates by factors of millions compared to uncatalyzed processes occurring through random molecular collisions alone. Protein folding relies on electromagnetic interactions between amino acid side chains that guide polypeptide chains into functional three-dimensional conformations through hydrophobic effects, hydrogen bonding, salt bridge formation, and van der Waals attractions that collectively encode structural information within amino acid sequences. Neural signal. Transmission depends on electrochemical gradients maintained by electromagnetic pumps that transport ions across cellular membranes, creating action potentials that propagate information throughout nervous systems at velocities determined by axon diameter, and myelination patterns that optimize electromagnetic signal propagation for rapid communication between distant brain regions. Vision operates through electromagnetic detection, where photons trigger conformational changes in rhodopsin proteins that initiate cascade reactions culminating in electrical signals or transmitted to visual cortex regions responsible for image processing and pattern recognition that enable conscious perception of electromagnetic radiation patterns reflecting off surrounding objects. Cellular communication involves electromagnetic signaling through hormone binding, neurotransmitter release, and gap junction coupling that coordinate multicellular organism development and homeostasis through information networks, operating across multiple spatial scales from molecular to organismal levels. Crystal growth demonstrates how electromagnetic forces organize matter into regular geometric patterns where ionic or atomic constituents arrange themselves according to electrostatic energy minimization principles that create ordered lattice structures extending across macroscopic dimensions through repetitive application of local electromagnetic interaction rules. Metamaterials exploit electromagnetic properties of artificially structured composites to create optical behaviors impossible with natural materials, including negative refractive indices, electromagnetic cloaking, and perfect lenses that manipulate photon propagation through engineered electromagnetic environments designed to control information flow in specific wavelength ranges. Quantum computing utilizes controlled electromagnetic interactions to manipulate quantum information encoded in atomic states, with laser pulses serving as logical gates that perform calculations through precisely timed electromagnetic field applications that preserve quantum coherence while enabling complex computational algorithms impossible with classical information processing systems. Electromagnetic spectrum analysis reveals chemical composition, temperature, velocity, magnetic field strength, and numerous other physical properties of distant astronomical objects through spectroscopic techniques that decode information carried by photons across cosmic distances spanning billions of light years, demonstrating how electromagnetic radiation serves as the primary information channel connecting Earth-based observers with the broader universe and enabling scientific understanding of cosmic evolution, stellar life cycle processes, galactic dynamics, and cosmological parameters that characterize the observable universe's large-scale structure and temporal development. What would happen if we could drain every last particle from a region of space and cool it to absolute zero, only to discover that this supposedly empty void still seethes with invisible activity that fundamentally challenges our understanding of nothingness itself? Zero-point energy represents one of quantum mechanics' most mind-bending consequences, revealing that electromagnetic fields retain residual vibrational energy even when cooled to their lowest possible state, creating a universe where true emptiness remains forever beyond physical reach. The quantum vacuum resembles a perfectly still pond surface that, upon closer inspection, teems with microscopic ripples, bubbles, and currents operating below normal perception thresholds, yet producing measurable effects on objects placed within this deceptively calm environment. Virtual photons spontaneously emerge from and disappear back into the quantum vacuum through processes permitted by Heisenberg. Uncertainty relations that allow temporary energy borrowing, provided such transactions resolve within time, intervals inversely proportional to the borrowed amounts. These ephemeral electromagnetic quanta exist too briefly for direct detection, but nonetheless mediate forces between distant charged particles through momentum exchanges that create attractive and repulsive interactions observable in countless laboratory experiments and astronomical phenomena. Quantum foam describes the texture of spacetime itself at Planck scale dimensions, where virtual particle pairs continuously pop in and out of existence, creating fluctuations in electromagnetic field strength that pervade every cubic centimeter of apparently empty space throughout the observable universe. The Casimir effect provides compelling experimental evidence for vacuum energy reality, demonstrating that two parallel conducting plates placed extremely close together experience attractive forces resulting from virtual photon pressure differences between interior and exterior regions surrounding the metallic surfaces. This phenomenon occurs because conducting boundaries modify the allowed wavelengths of virtual electromagnetic oscillations, creating fewer virtual photon modes between the plates compared to surrounding free space, which produces a net inward pressure that can be measured using sensitive force detection instruments. Laboratory demonstrations of Casimir forces confirm theoretical predictions with remarkable precision, validating quantum field theory calculations that initially seemed too bizarre to represent physical reality, yet now enable technological applications including micro-electromechanical systems and precision measurement devices. The electromagnetic field's ground state energy density, while finite for any bounded region, becomes infinite when integrated over all space, creating mathematical divergences that challenged early quantum electrodynamics until renormalization procedures were developed to extract meaningful finite predictions from seemingly nonsensical infinite quantities. The infinities reflect deep connections between quantum mechanics and spacetime geometry that continue puzzling theoretical physicists despite decades of successful practical applications ranging from laser technology to magnetic resonance imaging systems. Zero-point fluctuations influence atomic behavior through modifications of spontaneous emission rates, energy level shifts, and magnetic moment corrections that arise from virtual photon interactions with bound electrons orbiting atomic nuclei, producing measurable spectroscopic effects that confirm vacuum energy's role in determining atomic properties. The Lamb shift exemplifies how vacuum fluctuations create tiny but detectable changes in hydrogen atom energy levels that disagree with simpler quantum mechanical predictions, requiring incorporation of quantum electrodynamics effects to achieve theoretical agreement with experimental measurements. Spontaneous emission of photons by excited atoms depends fundamentally on vacuum, fluctuations that provide the electromagnetic field oscillations necessary to trigger transitions from higher to lower energy states, demonstrating that even basic atomic physics phenomena rely on virtual particle interactions within the quantum vacuum. Dynamic Casimir effects occur when rapidly changing boundary conditions modulate vacuum fluctuations strongly enough to convert virtual photons into real particles detectable through conventional measurement techniques, effectively creating electromagnetic radiation from purely geometric manipulations of empty space. Vacuum birefringence represents another subtle consequence of quantum fluctuations, where intense electromagnetic fields temporarily polarize the vacuum through virtual electron-positron pair creation, causing modifications in light propagation that become measurable using powerful laser systems or astronomical observations of neutron star magnetic fields. Hawking radiation near black hole event horizons exploits vacuum fluctuations to generate thermal photon emission through processes where gravitational tidal forces separate virtual particle pairs, allowing one member to escape while the other falls into the black hole, thereby extracting energy from the vacuum through gravitational interactions. Cosmological implications of vacuum energy include contributions to the universal expansion rate and possible connections to dark energy phenomena that currently accelerate cosmic expansion according to observational evidence from distant supernovae and cosmic microwave background measurements. Quantum field theory suggests that vacuum energy density should be enormous, yet astronomical observations indicate much smaller values, creating the cosmological constant problem that represents one of modern physics' most significant unsolved puzzles regarding the relationship between microscopic quantum effects and macroscopic gravitational phenomena operating on cosmic scales throughout universal evolution. How can particles that exist for impossibly brief moments and can never be directly detected nonetheless produce the electromagnetic forces that hold atoms together and enable every chemical reaction necessary for life itself? Virtual photons represent quantum mechanics' most paradoxical entities, existing as temporary disturbances in the electromagnetic field that mediate interactions between charged particles through momentum transfer processes occurring faster than the uncertainty principle permits direct observation. These ephemeral messengers constantly shuttle between electrons, protons, and other charged objects, carrying force information that creates attractions between opposite charges and repulsions between similar charges through exchanges that happen billions of times per second, yet remain completely invisible to experimental detection. The concept emerges from quantum field theory's marriage with special relativity, where electromagnetic interactions must propagate at finite speeds while maintaining causal relationships between distant events, requiring force-carrying particles to travel between interacting objects, rather than permitting instantaneous action at distance forbidden by relativistic principles. Virtual photon exchanges create the electrostatic forces binding electrons to atomic nuclei, establishing chemical bonds between atoms and generating magnetic interactions between current-carrying conductors through processes that operate continuously throughout the material world, despite involving particles that technically violate energy conservation during their brief existences. Feynman diagrams provide elegant visual maps of these virtual particle interactions, depicting how incoming particles exchange momentum through virtual photon emissions and absorptions that redirect their trajectories according to electromagnetic force laws, while conserving overall energy, momentum, and electric charge throughout the complete interaction process. These diagrammatic representations transform complex quantum field theory calculations into manageable mathematical procedures that enable precise predictions about interaction cross-sections, scattering angles, and reaction probabilities observable in particle accelerator experiments and atomic physics measurements. The analogy of invisible messengers constantly passing between charged objects captures the essence of virtual photon behavior, where electromagnetic communications occur through particle exchanges that remain undetectable individually, yet produce cumulative effects observable as macroscopic forces governing everything from molecular structure to planetary motions. Consider how electrons orbiting atomic nuclei maintain their bound states through continuous virtual photon exchanges with positively charged protons that create attractive forces sufficient to overcome electron kinetic energy, while permitting quantum mechanical orbital motion that prevents spiral collapse into nuclear cores. Chemical bonding relies entirely on virtual electromagnetic interactions where electron clouds around different atomic nuclei overlap and exchange virtual photons that either stabilize shared electron configurations in covalent bonds or facilitate electron transfer in ionic compounds through electrostatic attractions mediated by virtual particle exchanges. Magnetic forces between current-carrying wires result from virtual photon exchanges between moving charges that carry information about particle velocities and create velocity-dependent force components perpendicular to both current directions and magnetic field orientations according to relativistic electromagnetic theory. Van der Waals attractions between electrically neutral molecules arise from virtual photon exchanges involving temporary charge fluctuations that create instantaneous dipole moments, subsequently inducing complementary dipoles in neighboring molecules, generating weak but measurable attractive forces responsible for liquid cohesion and gas condensation phenomena. Quantum electrodynamics calculations involving virtual photon loops achieve extraordinary theoretical precision, predicting the electron's anomalous magnetic moment to more than 10 decimal places through mathematical procedures that sum contributions from increasingly complex virtual particle interaction diagrams representing all possible ways electromagnetic forces can operate between charged particles. The reality of virtual interactions manifests through measurable effects, including the Lamb shift in hydrogen atom energy levels, corrections to electron gyromagnetic ratios, and modifications of interaction rates for various atomic transitions that arise from virtual photon contributions to electromagnetic field fluctuations surrounding charged particles. Superconductivity demonstrates how virtual photon exchanges can create macroscopic quantum coherence effects, where electron pairs coupled through phonon-mediated virtual interaction flow through crystalline lattices without electrical resistance, enabling perfect current conduction and magnetic field expulsion that violates classical electromagnetic expectations. Everyday electronic devices from transistors to computer processors depend fundamentally on virtual photon-mediated electromagnetic interactions that control electron flow through semiconductor materials, creating the switching and amplification behaviors essential for digital information processing and modern technology. Virtual photon exchanges occur even between distant astronomical objects, with electromagnetic forces between charged particles in stellar plasmas, planetary magnetospheres, and interstellar media operating through identical virtual particle mechanisms that create aurora displays, radiation belt dynamics, and cosmic ray acceleration processes observable throughout the universe. The spontaneous emission of real photons by excited atoms requires virtual electromagnetic field fluctuations to provide the initial perturbation that triggers transitions from higher to lower energy states, demonstrating how virtual particles enable the creation of detectable radiation through processes that would be impossible without quantum vacuum contributions to atomic physics. What happens when the most successful theory in physics history produces mathematical calculations that yield infinite results for quantities that must obviously be finite in physical reality? Quantum field theory encounters fundamental mathematical difficulties where certain calculations involving virtual particle loops generate divergent integrals that approach infinity, creating a crisis where theoretical predictions become meaningless despite the understanding framework's extraordinary success in describing electromagnetic phenomena with unprecedented precision. These infinities arise when physicists attempt to calculate corrections to particle properties caused by virtual photon interactions, discovering that summing contributions from virtual particles with arbitrarily high energies produces mathematical expressions that grow without bound rather than converging to sensible finite values. The energy density of quantum vacuum fluctuations, when integrated over all possible wavelengths, yields an infinite result that would imply infinite energy content throughout space, contradicting obvious physical requirements for finite energy densities in any realistic universe. Early pioneers of quantum electrodynamics faced the daunting challenge of extracting meaningful predictions from mathematical formalism that seemed fundamentally flawed due to these divergence problems that threatened to invalidate the entire theoretical enterprise despite its remarkable agreement with experimental observations in simpler calculations. Renormalization emerged as a sophisticated mathematical procedure for taming these infinities through systematic redefinition of fundamental parameters including particle masses, charges, and coupling constants in ways that absorb infinite contributions into unmeasurable quantities while preserving finite predictions for observable phenomena. This process involves separating calculations into finite parts that correspond to measurable effects and infinite parts that get absorbed into parameter redefinitions, essentially hiding the problematic infinities within theoretical constructs that cannot be directly observed or measured through experimental techniques. The renormalization procedure resembles finding finite answers within mathematical expressions containing infinite terms by carefully rearranging equations to isolate divergent contributions and incorporating them into fundamental constants whose precise values must be determined through experiment rather than theoretical calculation alone. Physicists discovered that only certain types of quantum field theories can be successfully renormalized, with renormalizable theories requiring that all infinities can be absorbed through redefinitions of a finite number of parameters, while non-renormalizable theories generate new types of divergences that cannot be eliminated through any systematic procedure. The standard model of particle physics represents a renormalizable theory where electromagnetic, weak nuclear, and strong nuclear interactions can all be described through mathematical frameworks that successfully eliminate infinities, while producing finite predictions that match experimental measurements with extraordinary accuracy across numerous energy scales and interaction types. Despite renormalization's practical success, the fundamental reason why this mathematical procedure works remains one of theoretical physics' deepest mysteries, suggesting either that our mathematical tools are inadequate for describing quantum reality, or that physical laws themselves possess subtle structures not yet fully understood by current theoretical frameworks. The effective field theory approach provides partial insight into renormalization's success by recognizing that quantum field theories represent approximate descriptions valid only within limited energy ranges, with high-energy physics contributions that generate problematic infinities potentially arising from unknown physical phenomena operating beyond current theoretical knowledge. Cutoff procedures introduce artificial energy scales above which virtual particle contributions are ignored, effectively truncating infinite integrals at finite values, while acknowledging that such mathematical manipulations may reflect genuine physical processes that limit virtual particle energies through mechanisms not incorporated into current theoretical models. The cosmological constant problem exemplifies renormalization difficulties on cosmic scales, where quantum field theory predictions for vacuum energy density exceed observational bounds by more than 100 orders of magnitude, suggesting fundamental gaps in understanding how quantum mechanics and general relativity interface at macroscopic scales. Loop calculations in quantum electrodynamics require increasingly sophisticated mathematical techniques to handle higher-order corrections involving multiple virtual particle exchanges, with each additional loop generating more complex divergent structures that test the limits of renormalization procedures, while potentially revealing new physical insights about electromagnetic interaction mechanisms. Dimensional regularization represents one elegant approach to managing infinities by performing calculations in non-integer spatial dimensions where divergent integrals become finite, subsequently taking limits as dimensions approach physically meaningful values while carefully tracking how infinite contributions emerge during this limiting process. The philosophical implications of renormalization challenge traditional notions about mathematical completeness in physical theories, suggesting that fundamental descriptions of nature might necessarily involve procedures that seem mathematically ad hoc, yet nonetheless produce correct predictions about natural phenomena through mechanisms that transcend conventional logical frameworks. Computer simulations of quantum field theory calculations on discrete space-time lattices provide alternative approaches to infinite continuum integrals, replacing continuous integration with finite summation procedures that naturally avoid divergence problems, while potentially revealing whether infinities represent genuine features of physical reality or artifacts of idealized mathematical approximations to discrete underlying structures. Could the future somehow reach backward through time to influence past events, creating a universe where quantum measurements determine not just present reality, but also reshape the history that led to current observations? Modern single-photon experiments reveal one of quantum mechanics' most unsettling implications. The behavior of individual photons depends fundamentally on measurement choices that experimenters make even after the particles have already passed through apparatus and completed their journeys to detection screens. These sophisticated investigations use extremely sensitive photodetectors capable of registering individual electromagnetic quanta, enabling researchers to study wave-particle duality phenomena one photon at a time rather than relying on statistical patterns from large ensembles of particles that might obscure subtle quantum mechanical effects. When scientists install which-way detectors near the slits in double-slit experiments, these monitoring devices immediately destroy interference patterns regardless of whether the collected pathway information gets recorded, analyzed, or even observed by human investigators, suggesting that the mere possibility of obtaining path information fundamentally alters photon behavior. The elimination of interference occurs instantaneously upon detector activation, transforming wave-like photons exhibiting self-interference into particle-like entities following definite trajectories through specific slits, demonstrating that quantum measurement represents an active process that participates in creating observed reality rather than passively revealing pre-existing properties. Delayed choice experiments push this phenomenon into even stranger territory by implementing measurement decisions after photons have already travelled through the experimental apparatus, revealing that retroactive choices about whether to measure particle or wave properties somehow influence how those photons behave during earlier portions of their journeys. John Wheeler proposed the ultimate delayed choice scenario involving cosmic scale interferometry, where light from distant quasars gets split by gravitational lensing around intervening galaxies, creating separate pathways that converge at Earth-based telescopes billions of years after the photons began their journeys across intergalactic space. In Wheeler's thought experiment, astronomers could decide whether to observe interference between the two light paths or to determine which gravitational lens each photon traversed, with this measurement choice apparently reaching backward across cosmic time to influence photon behavior that occurred before Earth existed as a planet. This scenario suggests that quantum measurement effects operate independently of spatial and temporal separation scales, creating causal relationships that challenge conventional understanding about the relationship between past, present, and future events in physical systems governed by quantum mechanical principles. The analogy of a story whose ending changes its beginning captures this temporal paradox beautifully, where narrative conclusions retroactively determine plot elements that supposedly led to those outcomes, creating logical loops that violate classical causality while remaining consistent with quantum mechanical predictions about measurement-dependent reality. Retrocausality emerges as a potential explanation for these phenomena, proposing that quantum systems exhibit backward-in-time influences that allow future measurement choices to affect past quantum states through mechanisms that preserve overall causal consistency while permitting apparent violations of temporal ordering at microscopic scales. Quantum eraser experiments demonstrate even more subtle aspects of this temporal puzzle by showing that interference patterns can be restored even after which-way information has been obtained, provided that pathway data gets subsequently destroyed or rendered inaccessible through additional quantum mechanical manipulations that erase the distinguishability between different photon trajectories. These erasure processes work regardless of when they occur relative to initial photon detection, suggesting that quantum information about particle paths can be retroactively modified through measurements performed on quantum systems that were entangled with the original photons during their passage through experimental apparatus. The implications extend far beyond laboratory demonstrations into fundamental questions about the nature of time itself, suggesting that quantum mechanics might require abandoning linear temporal progression in favor of block universe models where past, present, and future events exist simultaneously within eternal space-time structures that permit bidirectional causal influences between different temporal locations. Quantum field theory provides mathematical frameworks for describing these apparent temporal paradoxes through advanced and retarded Green's functions that incorporate both forward and backward time propagation of quantum information, creating theoretical structures where future boundary conditions can influence past field configurations through complex, mathematical relationships that preserve overall consistency. Bell inequality violations in quantum entanglement experiments reveal related phenomena where measurement choices at one location immediately affect quantum states at distant locations, suggesting that quantum correlations transcend classical space-time limitations and operate through mechanisms that connect spatially and temporally separated events through non-local quantum mechanical relationships. The philosophical implications challenge fundamental assumptions about objective reality, free will, and determinism by suggesting that conscious measurement choices might retroactively determine historical facts about quantum systems, creating participatory universe models where observers play active roles in constructing the past through present decision-making processes that somehow influence previous quantum mechanical outcomes across arbitrary temporal intervals. What happens when scientists discover they can retroactively erase pathway information that has already been recorded, magically restoring wave interference patterns long after photons have been detected as individual particles. Quantum eraser experiments reveal that information itself plays a fundamental role in determining quantum mechanical outcomes, with the mere existence or destruction of distinguishing data about particle trajectories immediately affecting whether photons exhibit wave-like or particle-like characteristics regardless of temporal sequence between detection and information manipulation. These sophisticated investigations demonstrate that interference patterns depend not on whether experimenters actually observe which-way information, but rather on whether such data could theoretically be obtained from quantum systems involved in the measurement process, suggesting that potential knowledge rather than actual knowledge governs quantum mechanical behavior. The principle operates through quantum entanglement between photons and auxiliary systems that initially record pathway information, creating correlated states where manipulating the auxiliary systems retroactively affects the interference visibility of previously detected photons through non-local quantum correlations that transcend classical spacetime limitations. Distinguishable quantum paths occur when photons carry internal markers such as polarization states, or frequency tags that enable theoretical identification of which trajectory each particle followed through experimental apparatus, while indistinguishable paths involve photons with identical properties that cannot be differentiated through any measurement procedure, even in principle. Information erasure proceeds by performing measurements on entangled auxiliary systems that randomize or destroy the correlations between pathway markers and photon trajectories, effectively removing distinguishability, even though the original which-way data has already been permanently recorded in detector systems that cannot be directly modified. The quantum Cheshire cat phenomenon represents an even more bizarre manifestation of information effects, where properties of photons can be separated from the particles themselves through weak measurement techniques that partially extract information about quantum states without completely collapsing superposition configurations. Weak measurements enable simultaneous observation of complementary properties by trading measurement precision for minimal disturbance, allowing researchers to probe quantum systems gently enough to preserve coherence while obtaining statistical information about particle characteristics that would normally be mutually exclusive according to uncertainty principles. This process resembles observing a smile without seeing the cat that presumably created it, where photon properties such as momentum or polarization can be detected in spatial regions where the particles themselves are absent, challenging classical notions about property localization and suggesting that quantum characteristics possess independent existence from their material carriers. The separation occurs through carefully designed interferometric arrangements where photon wave functions split into multiple spatial components that carry different subsets of particle properties through distinct regions of experimental apparatus, enabling selective measurement of specific characteristics while preserving quantum coherence in unmeasured degrees of freedom. Pre-selection and post-selection procedures combined with weak measurement protocols create experimental conditions where photon properties appear displaced from their expected locations, with momentum measurements yielding finite values in regions where photon probability amplitudes approach zero, while position measurements indicate particle presence where momentum distributions become negligible. Information theory provides crucial insights into these phenomena by treating quantums, mechanical states as containers for information rather than classical objects with definite properties, revealing that measurement processes fundamentally involve information transfer between quantum systems rather than simple revelation of pre-existing characteristics through passive observation techniques. The destruction or preservation of distinguishing information becomes the key factor determining whether quantum superposition states collapse into definite outcomes or maintain coherence that enables continued interference effects, with information content rather than energy transfer governing the transition between quantum and classical behavior regimes. Delayed erasure experiments demonstrate that these information effects operate retroactively across arbitrary time intervals, allowing researchers to restore interference patterns minutes or even hours after initial photon detection by manipulating entangled systems that originally recorded pathway information through quantum, correlations that persist despite spatial and temporal separation. The fundamental role of information in quantum mechanics suggests that physical reality might be more accurately described as information processing rather than matter in motion, with particles representing informational structures that carry data about quantum states rather than substantial objects possessing intrinsic properties independent of measurement contexts. Quantum computing exploits these information-theoretic aspects of quantum mechanics by encoding computational data within quantum superposition states that can process multiple calculation branches simultaneously through parallel information pathways that eventually converge to yield enhanced computational capabilities compared to classical digital systems. The observer effect emerges as a consequence of thin information transfer requirements rather than consciousness-related phenomena, with measurement-induced decoherence occurring whenever quantum systems become informationally entangled with macroscopic environments that irreversibly record quantum state information through thermodynamically irreversible processes. Quantum cryptography utilizes the fundamental role of information in quantum mechanics to create communication protocols where eavesdropping attempts inevitably disturb transmitted quantum states, providing absolute security guarantees based on physical principles rather than computational complexity assumptions that could potentially be circumvented through advanced mathematical techniques. How can technologies that form the backbone of modern civilization function flawlessly, despite being built upon quantum mechanical principles that seem to violate common sense and defy classical understanding of physical reality? Lasers represent perhaps the most ubiquitous example of quantum paradox-dependent technology, operating through stimulated emission processes where coherent electromagnetic radiation emerges from quantums, mechanical population inversions that create more excited atoms than ground-state atoms within active laser media. This phenomenon requires precise manipulation of atomic energy levels using external pumping mechanisms that force electrons into metastable excited states, creating conditions where incoming photons trigger avalanche-like cascades of identical electromagnetic radiation through quantum mechanical resonance effects that amplify weak signals into powerful coherent beams. The resulting laser output exhibits perfect spatial and temporal coherence properties impossible to achieve through classical light sources, enabling applications ranging from precision surgery to fiber optic communications to compact disc players that depend fundamentally on quantum mechanical light-matter interactions for their operation. Quantum cryptography exploits fundamental quantum mechanical principles, including the no-cloning theorem and measurement-induced decoherence to create communication. Systems with absolute security guarantees based on physical laws rather than mathematical complexity. Assumptions that might eventually be circumvented through advanced computational techniques. Single photon sources generate individual electromagnetic quanta on demand through controlled atomic transitions, enabling quantum key distribution protocols where any eavesdropping attempt necessarily disturbs transmitted quantum states and reveals unauthorized interception through detectable changes in photon polarization statistics or error rates that exceed theoretical limits for secure transmission. Quantum radar systems utilize entangled photon pairs where one member of each pair gets transmitted toward target objects while its entangled partner remains at the detection facility, enabling target identification through quantum correlations that persist despite environmental noise and jamming attempts that would defeat conventional electromagnetic detection systems. Photovoltaic cells convert solar photons into electrical current through quantum mechanical photoelectric effects, where individual electromagnetic quanta excite electrons across semiconductor band gaps, creating electron-hole pairs that generate photovoltage when separated by built-in electric fields within carefully engineered junction structures that optimize quantum efficiency for specific wavelength ranges. Light-emitting diodes operate through reverse photoelectric processes where electrical current injection creates electron-hole recombination events that emit photons with wavelengths determined by semiconductor bandgap energies, enabling precise color control through quantum mechanical engineering of material composition and crystal structure parameters. Magnetic resonance imaging depends on quantum mechanical spin dynamics, where atomic nuclei precess in applied magnetic fields at frequencies proportional to field strength, with radiofrequency photons inducing spin-flip transitions that generate detectable electromagnetic signals encoding spatial information about tissue density and chemical composition throughout biological specimens. Quantum sensors achieve unprecedented measurement precision by exploiting quantum superposition states and entanglement effects that enable detection sensitivity approaching fundamental limits imposed by quantum mechanical uncertainty principles, with applications including gravitational wave detection, atomic clocks, and magnetometry systems that surpass classical measurement capabilities by orders of magnitude. The analogy of building bridges with materials that do not exist captures the essence of quantum technology development, where engineering applications successfully exploit phenomena that classical physics declares impossible, yet nonetheless produce reliable, reproducible results that enable countless practical applications throughout modern technological infrastructure. Quantum computing represents the ultimate expression of paradox-based technology, utilizing quantum superposition and entanglement to perform calculations that would require exponential time on classical computers, with quantum algorithms potentially revolutionizing cryptography, optimization, simulation, and machine learning through computational approaches that transcend classical information processing limitations. Superconducting quantum interference devices exploit macroscopic quantum coherence effects, where electrical currents flow without resistance through crystalline materials cooled below critical temperatures, creating magnetic field sensors with sensitivity sufficient to detect magnetic dipole moments from individual electrons or monitor neural activity within living brain tissue. Atomic fountains and optical lattices manipulate neutral atoms using precisely controlled laser fields that create artificial periodic potentials analogous to crystalline structures, enabling studies of quantum many-body physics and development of quantum simulators that model complex condensed matter phenomena impossible to analyze through classical computational methods. Quantum metrology utilizes entangled atomic ensembles to achieve measurement precision beyond standard quantum limits, with applications including tests of general relativity through detection of gravitational time dilation effects and searches for dark matter candidates through monitoring of atomic transition frequencies that might be affected by exotic particle interactions. Single photon detectors based on superconducting nanowires or avalanche photodiodes enable detection of individual electromagnetic quanta with near-perfect efficiency, supporting quantum communication experiments and enabling astronomical observations of extremely faint celestial objects through photon counting techniques that extract maximum information from minimal light levels available from distant cosmic sources. What if the very question of whether reality exists independently of observation reveals more about the limitations of human language than about the fundamental nature of existence itself? Different interpretations of quantum mechanics offer radically distinct answers to this question, each proposing alternative frameworks for understanding how photon measurements transform potential outcomes into definite results while preserving mathematical consistency with experimental observations. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems exist in superposition states encompassing multiple possibilities simultaneously until measurement interactions collapse these probabilistic configurations into single definite outcomes that constitute the only meaningful reality accessible to scientific investigation. This framework treats quantum mechanical wave functions as mathematical tools for calculating measurement probabilities rather than descriptions of objective physical properties, implying that questions about photon behavior between measurements become meaningless because unmeasured quantum systems possess no definite characteristics independent of experimental contexts. Many worlds interpretation, proposed by Hugh Everett, offers a dramatically different perspective where all possible quantum outcomes occur simultaneously within parallel universe branches that continuously proliferate whenever quantum systems encounter measurement-like interactions that split reality into multiple coexisting versions of cosmic history. According to this framework, every quantum measurement creates additional universe branches containing all possible results, with conscious observers experiencing only single branches while remaining unaware of alternative realities where different outcomes occurred for identical experimental configurations. The role of consciousness in quantum mechanics remains one of the most controversial aspects of foundational debates, with some interpretations suggesting that conscious observation plays a fundamental role in collapsing quantum superpositions, while others argue that any interaction capable of recording information produces identical effects regardless of whether conscious beings participate in or observe the measurement process. Careful examination reveals that quantum mechanical equations make no explicit reference to consciousness, instead describing measurement as physical interaction between quantum systems and macroscopic apparatus that creates irreversible records of quantum state information through thermodynamically driven decoherence processes. The analogy of reality as a story told during observation captures how quantum measurement resembles narrative creation, where plot elements emerge through the telling rather than existing as predetermined facts awaiting discovery, suggesting that physical reality possesses similar participatory characteristics where measurement interactions actively construct observable phenomena. Objective collapse. Theories propose that quantum superposition states undergo spontaneous reduction according to stochastic processes that occur naturally without external measurement, creating modified quantum mechanics where reality crystallizes through random events rather than deterministic measurement interactions while preserving agreement with experimental observations. Hidden variable theories attempt to restore classical realism by proposing that quantum systems possess definite properties at all times, with apparent randomness and measurement dependence arising from incomplete knowledge about underlying deterministic variables that govern system behavior according to classical physics principles extended into microscopic domains. Bell's theorem and associated experimental tests demonstrate that any hidden variable theory consistent with quantum mechanical predictions must exhibit non-locality, meaning that measurement choices at one location immediately influence outcomes at distant locations through mechanisms that transcend classical space-time limitations and suggest fundamental interconnectedness throughout physical reality. Relational interpretation treats quantum mechanical properties as meaningful only within specific measurement contexts, rather than absolute characteristics of isolated systems, proposing that photon behavior depends fundamentally on relationships between observer and observed rather than intrinsic particle properties that exist independently of experimental arrangements. The comfort of living with fundamental mysteries emerges from recognizing that scientific progress often involves embracing rather than eliminating conceptual puzzles, with quantum mechanics demonstrating how mathematical precision and experimental success can coexist with profound philosophical uncertainties about the nature of physical reality. Decoherence theory explains how quantum superpositions become effectively classical through environmental interactions that entangle quantum systems with surrounding thermal baths, creating apparent wave function collapse without requiring fundamental modifications to quantum mechanical equations or special roles for conscious observers. Information theoretic interpretations focus on quantum mechanics as fundamentally concerned with information processing rather than material objects, treating measurement as information transfer between quantum systems rather than revelation of pre-existing properties through passive observation techniques that leave measured systems unchanged. Quantum Bayesianism reframes quantum probabilities as subjective degrees of belief held by individual observers rather than objective features of physical systems, suggesting that quantum mechanics describes optimal betting strategies for predicting measurement outcomes, rather than providing complete descriptions of mind-independent reality. The philosophical implications extend beyond academic debates into practical questions about scientific methodology, technological development, and humanity's relationship with natural world, suggesting that quantum mechanics challenges traditional boundaries between observer and observed, while opening new perspectives on consciousness, causality, and cosmic evolution that may ultimately transform human understanding of existence itself. Why does the act of observation at quantum scales seem to dissolve the traditional boundary between scientist and subject, transforming neutral investigation into active participation that helps create the very phenomena being studied? The measurement problem in quantum mechanics reveals that classical distinctions between observer and observed become meaningless when dealing with photons and other quantum entities, where detection processes inevitably disturb measured systems through momentum transfer, energy exchange, and information entanglement that fundamentally alter quantum states rather than simply revealing pre-existing properties. Classical intuition fails spectacularly at microscopic scales because our everyday experience involves macroscopic objects containing trillions of particles where individual quantum effects average out into predictable classical behavior, providing no preparation for encountering phenomena where single particles exist in multiple states simultaneously until specific interactions force them into definite configurations. The participatory universe concept emerges from recognizing that observers cannot be separated from experimental apparatus and quantum systems being studied, creating unified observer-observed instrument complexes where measurement outcomes depend on the complete configuration of all components rather than properties attributed solely to isolated quantum particles. Bell's theorem delivers the death blow to local realism by proving mathematically that any theory reproducing quantum mechanical predictions must violate either locality or realism, with experimental tests consistently supporting quantum mechanics and demonstrating that entangled photons exhibit correlations impossible to explain through classical physics mechanisms involving local hidden variables. Local realism assumes that objects possess definite properties independent of measurement, and that influences cannot travel faster than light. Yet quantum mechanics violates these assumptions through instantaneous correlations between distant entangled particles that respond to measurement choices made on their partners, regardless of spatial separation distances that would require superluminal communication in classical frameworks. The analogy of being simultaneously audience and actor in reality's performance captures how quantum measurement transforms passive observation into active participation, where experimental choices partially determine which aspects of quantum reality become manifest through measurement interactions that create rather than merely reveal observable phenomena. Complementarity emerges as fundamental feature rather than temporary limitation, with Niels Bohr recognizing that complete understanding of quantum systems requires multiple mutually exclusive descriptions that cannot be unified into single classical pictures, yet together provide comprehensive knowledge about quantum behavior under different experimental conditions. Wave and particle descriptions represent complementary perspectives on a photon behavior rather than contradictory accounts of identical phenomena, with experimental arrangements determining which aspects become accessible to measurement, while necessarily obscuring complementary properties according to uncertainty principle constraints that limit simultaneous knowledge acquisition. The embrace of complementarity requires abandoning demands for complete classical visualization of quantum phenomena in favor of accepting that nature operates according to principles fundamentally different from macroscopic intuition, while maintaining mathematical precision and experimental predictability through quantum mechanical formalism. Measurement-induced decoherence explains how quantum superposition states effectively collapse when quantum systems become entangled with macroscopic environments containing vast numbers of degrees of freedom that irreversibly record quantum state information through thermodynamically driven processes that select specific outcomes from superposition configurations. The emergence of classical behavior from quantum foundations occurs through environmental interaction, rather than fundamental changes in physical laws, with apparent wave function collapse representing effective description of complex quantum evolution rather than new physics beyond standard quantum mechanical principles. Observer effects extend beyond direct measurement interactions to include any process capable of distinguishing between alternative quantum states through information extraction that correlates system properties with external records regardless of whether conscious beings participate in or monitor these correlation-creating interactions. Quantum contextuality demonstrates that measurement outcomes depend on complete experimental contexts rather than isolated system properties, with photon behavior determined by entire measurement apparatus configurations, including unperformed alternative measurements that could theoretically be conducted using the same equipment arrangements. The dissolution of subject-object dualism in quantum mechanics suggests broader philosophical implications about consciousness, perception, and knowledge that extend beyond physics into questions about human relationship with natural world and limits of scientific objectivity in describing phenomena where observers necessarily participate in creating observed reality. Retrocausal interpretations propose that measurement choices influence past quantum states through backward-in-time effects that preserve overall causal consistency while allowing future decisions to determine historical quantum mechanical outcomes through mechanisms that operate independently of classical temporal ordering constraints. Quantum information theory treats measurement as information transfer between correlated systems rather than property revelation through passive detection, with observable outcomes emerging from information processing operations that transform potential data encoded in superposition states into definite results, accessible to classical recording devices and conscious observers who interpret measurement records according to established scientific protocols and theoretical frameworks. How might embracing quantum mechanical insights about uncertainty and paradox transform our approach to everyday challenges, relationships, and decisions that seem to demand clear-cut answers in a world that may be fundamentally more mysterious and interconnected than we typically acknowledge? Accepting paradox and contradiction becomes not just intellectually honest but practically beneficial when we recognize that photon behavior demonstrates how a apparently conflicting descriptions can simultaneously be true depending on perspective and context, suggesting that many human dilemmas might benefit from complementary thinking rather than forced resolution into single coherent narratives. The beauty of not knowing everything emerges when we stop treating uncertainty as failure and instead appreciate it as an invitation to remain curious, flexible, and open to new possibilities that couldn't exist if every aspect of reality were predetermined and completely comprehensible through current knowledge frameworks. Quantum thinking fundamentally alters perspectives on uncertainty by revealing that even the most successful scientific theory in history operates through probability calculations rather than deterministic predictions, encouraging humility about our ability to control outcomes while maintaining confidence in our capacity to influence favourable statistical trends through thoughtful preparation and adaptive responses. The interconnectedness revealed by quantum entanglement suggests that individual particles can maintain instantaneous correlations across arbitrary distances through mechanisms that transcend classical space-time limitations, offering metaphorical insights into human relationships where emotional connections, shared experiences, and mutual influences might operate through channels more subtle and profound than direct communication or physical proximity. Living comfortably with uncertainty requires developing tolerance for ambiguity without abandoning rational analysis, much like quantum physicists who make precise calculations involving fundamental randomness, while accepting that complete predictive control remains forever beyond reach regardless of theoretical sophistication or technological advancement. The analogy of dancing with mystery rather than demanding answers captures how quantum mechanics teaches scientists to work productively with phenomena that resist complete explanation while yielding remarkable technological applications and deeper insights into natural processes that become more fascinating rather than less mysterious as understanding develops. Quantum superposition suggests that holding multiple contradictory possibilities simultaneously might be more realistic than forcing premature decisions that collapse rich potential into limited actual outcomes, encouraging patience with complex situations that may require time and additional information before optimal responses become apparent through natural evolution. Measurement effects in quantum mechanics demonstrate how observation inevitably influences observed systems, reminding us that our presence and attention alter social dynamics, family relationships, and professional interactions in ways that should inspire mindful consideration of how our investigative approaches shape the realities we encounter. The observer effect encourages humility about objective knowledge by revealing that complete separation between knower and known becomes impossible when dealing with complex systems where measurement tools, observational perspectives, and measurement timing fundamentally influence experimental outcomes through unavoidable interactions. Complementarity principles suggest that conflicting viewpoints about personal relationships, political issues, or career decisions might reflect different aspects of multifaceted realities, rather than incompatible truths requiring victory for one perspective at the expense of all alternatives, opening possibilities for synthesis approaches that honor multiple valid insights. Wave-particle duality demonstrates how identical phenomena can manifest completely different characteristics depending on how we choose to examine them, encouraging flexible thinking about human personalities, organizational cultures, and social problems that might benefit from multiple analytical approaches rather than rigid categorical thinking that forces complex realities into oversimplified frameworks. Quantum field theory's revelation that apparent emptiness contains dynamic activity suggests that periods of apparent stagnation in personal growth, creative projects, or relationship development might conceal important preparation work occurring below conscious awareness thresholds, encouraging patience and trust in natural processes rather than forced acceleration. Entanglement phenomena indicate that actions affecting one part of a quantum system immediately influence distant components through non-local correlations, inspiring consideration of how individual choices ripple through families, communities, and ecosystems in ways that extend far beyond immediate visible consequences through interconnected networks of influence and mutual dependence. Uncertainty principles establish fundamental limits on simultaneous knowledge acquisition, suggesting that attempting to control all aspects of complex situations simultaneously might be counterproductive compared to strategic focus on specific goals, while accepting that other variables will necessarily remain undetermined until additional information becomes available through patient observation. Quantum coherence effects require delicate environmental conditions that preserve superposition states against decoherence inducing disturbances, offering insights about maintaining creative inspiration, meditative awareness, and relationship harmony through careful attention to environmental factors that either support or undermine subtle states of consciousness and emotional connection that enable extraordinary human experiences and achievements. How can we now understand that our entire exploration has revealed light not as mere illumination, but as the fundamental creative principle that weaves the fabric of existence, from pure nothingness into the rich tapestry of material reality? Synthesizing this remarkable journey through quantum mechanics reveals photons as far more than simple energy carriers, emerging instead as the primary architects of cosmic structure, whose massless nature paradoxically enables them to construct the massive universe of stars, planets, atoms, and living organisms through electromagnetic interactions that mediate virtually every physical process throughout space and time. The electromagnetic field emerges as the universe's foundational substrate, an invisible ocean of potential energy that pervades every location in spacetime, while supporting the propagation of photons that carry information, transport energy, and facilitate the formation of complex structures from the simplest quantum interactions to the most elaborate biological systems. Massless particles build massive reality through processes that transform pure electromagnetic energy into matter via pair production, mediate gravitational phenomena through radiation pressure effects, enable stellar nucleosynthesis reactions that forge heavy elements from primordial hydrogen, and power the chemical processes that sustain life through photosynthetic conversion of solar radiation into biological energy storage molecules. Photons serve simultaneously as cosmic messengers broadcasting information about distant galaxies, stellar compositions, and universal evolution, while also functioning as active participants in reality construction through their roles in atomic bonding, molecular formation, and the electromagnetic forces that determine material properties throughout the observable universe. The beautiful impossibility of nothing creating everything becomes comprehensible when we recognize that quantum field theory reveals apparent emptiness as seething with virtual particle activity, where electromagnetic fluctuations provide the dynamic foundation from which real particles emerge through energy, concentration processes that convert field oscillations into measurable quanta. Virtual photons mediating electromagnetic interactions between charged particles demonstrate how forces themselves arise from exchanges of massless entities that exist too briefly for direct detection, yet produce all the attractions and repulsions responsible for atomic structure, chemical bonding, and material stability throughout cosmic evolution. Zero-point energy fluctuations ensure that true nothingness remains impossible in quantum mechanics, with vacuum states containing residual electromagnetic activity that influences atomic transition rates, creates measurable forces between conducting surfaces, and provides the quantum foundation for spontaneous emission processes that enable stars to shine and atoms to release energy through radiative transitions. The original paradox gains deeper appreciation as we understand that photon mass equals zero precisely because these particles represent pure energy, in motion rather than substantial entities carrying energy as additional cargo, with their existence depending entirely on maintaining light-speed velocity that would become impossible if they possessed even infinitesimal rest mass. Electromagnetic radiation creates the communication network enabling complex organization throughout the universe, from quantum information transfer between atomic constituents through chemical signaling in biological systems to electromagnetic wave propagation across galactic distances, that connects all regions of spacetime through shared participation in cosmic electromagnetic phenomena. The wave-particle duality that initially seemed contradictory now appears as complementary aspects of a deeper quantum reality, where photons embody both discrete energy packets, enabling quantized interactions, and continuous wave phenomena, supporting interference effects that demonstrate the underlying field nature of electromagnetic radiation. Creation and annihilation. Operators in quantum field theory provide mathematical descriptions of how photons spontaneously appear from and disappear back into the electromagnetic vacuum through processes that maintain energy conservation, while permitting temporary fluctuations according to uncertainty principle, constraints that govern all quantum mechanical systems. Pair production demonstrates the ultimate expression of electromagnetic creativity, where high-energy photons transform directly into matter, antimatter, pairs, through interactions that literally convert pure radiation into substantial particles possessing definite mass, electric charge, and spin characteristics completely absent from their massless electromagnetic predecessors. The cosmic significance extends from Big Bang nucleosynthesis, powered by electromagnetic interactions through stellar evolution, driven by radiative energy transport to the formation of complex chemistry, enabling biological evolution through photosynthetic processes that capture solar electromagnetic energy and convert it into chemical bonds supporting terrestrial life. Photons as fundamental creative forces operate across all scales, from quantum mechanical interactions determining atomic structure, through electromagnetic phenomena governing planetary dynamics, to cosmic ray acceleration processes involving electromagnetic fields spanning galactic distances and influencing universal evolution through mechanisms that demonstrate the central role of massless particles in constructing massive reality. The journey concludes with profound appreciation for how these impossible entities that weigh nothing yet accomplish everything reveal the universe as far more strange, beautiful, and creative than classical physics could have imagined, inspiring wonder at the elegant mathematical relationships governing electromagnetic phenomena that enable conscious beings to contemplate the very photons whose interactions created the conditions necessary for awareness, intelligence, and scientific understanding to emerge from cosmic evolution. What profound mysteries about photons continue to challenge the world's most brilliant physicists despite decades of extraordinary experimental success and theoretical precision that has yielded technologies transforming human civilization? Current research in quantum electrodynamics pushes the boundaries of understanding through investigations into quantum field fluctuations at unprecedented energy scales, exploring how electromagnetic interactions behave under extreme conditions involving intense laser fields, ultra-short pulse durations, and non-linear optical phenomena that reveal new aspects of photon behavior beyond traditional, perturbative calculations. Scientists are actively investigating whether photons might possess infinitesimally small but non-zero rest masses through precision measurements of electromagnetic wave propagation velocities across cosmic distances, searching for frequency-dependent variations that would indicate departures from exact masslessness while maintaining consistency with special relativity and gauge theory requirements. The search for quantum gravity represents one of modern physics' most ambitious goals, attempting to unify electromagnetic interactions described by quantum field theory with gravitational phenomena governed by general relativity through theoretical frameworks such as string theory, loop quantum gravity, and emergent spacetime models that may fundamentally alter our understanding of photon propagation through curved spacetime. Vacuum birefringence experiments probe whether intense electromagnetic fields can polarize empty space through virtual particle effects that create anisotropic optical properties in regions of strong electromagnetic radiation, testing quantum electrodynamics predictions about nonlinear vacuum responses that remain at the edge of experimental detectability using current technological capabilities. The hierarchy problem in particle physics questions why electromagnetic interactions are so much stronger than gravitational forces, with photons mediating electromagnetic phenomena billions of times more effectively than hypothetical gravitons mediate gravitational interactions through mechanisms that remain unexplained despite extensive theoretical investigations into extra dimensions, supersymmetry, and modified gravity theories. Dark photon research explores whether additional gauge bosons similar to ordinary photons might exist with slightly different property that could explain dark matter, phenomena, cosmological constant problems, or anomalous experimental results that suggest physics beyond the standard model, through hidden sector interactions involving photon-like particles with altered coupling strengths. Quantum coherence preservation in macroscopic systems continues challenging researchers who seek to understand how electromagnetic interactions maintain quantum superposition states, despite environmental decoherence effects, with potential applications to quantum computing, sensing technologies, and fundamental tests of quantum mechanics at increasingly large scales approaching classical boundaries. The measurement problem remains unresolved despite quantum electrodynamics' phenomenal success, with ongoing debates about whether photon wave function collapse represents genuine physical processes or emergent phenomena arising from complex quantum dynamics involving macroscopic measurement apparatus that irreversibly record quantum information through thermodynamically driven evolution. Entanglement generation and distribution through photonic networks face technical challenges related to maintaining quantum correlations over extended distances, while minimizing decoherence effects from environmental interactions, fiber optic losses, and detector inefficiencies that currently limit practical quantum communication applications despite promising theoretical foundations and proof-of-principle demonstrations. The cosmological constant problem represents perhaps the deepest mystery connecting photon physics to universal evolution, where quantum field theory predictions for vacuum energy density exceed observational bounds by more than 100 orders of magnitude, suggesting fundamental gaps in understanding how electromagnetic zero-point fluctuations relate to cosmic expansion and space-time geometry. Mystery emerges not as failure, but as an essential feature of scientific progress that drives continued investigation, technological innovation, and theoretical development through recognition that each answered question reveals new layers of complexity requiring fresh experimental approaches and conceptual frameworks to address previously unconsidered phenomena. The joy of eternal questions in physics reflects how photon research consistently generates more fascinating puzzles than it solves, creating expanding frontiers of knowledge where each breakthrough opens additional research directions while demonstrating that natural phenomena possess depths exceeding current theoretical capabilities and experimental technologies. Quantum field theory's mathematical infinities continue challenging theoretical physicists who seek deeper understanding of renormalization procedures that successfully eliminate divergent calculations, while potentially indicating unknown physics operating at energy scales beyond current experimental reach through mechanisms that may require revolutionary conceptual advances comparable to the transition from classical to quantum mechanics. Consciousness-related questions about quantum measurement and observation effects remain scientifically contentious despite popular speculation, with ongoing research focusing on decoherence timescales, information processing in biological systems, and the role of classical quantum boundaries in determining when and how quantum superposition states effectively collapse into definite measurement outcomes accessible to macroscopic recording devices and conscious observers. An invitation to continued wonder emerges naturally from recognizing that photon physics exemplifies how scientific understanding enhances rather than diminishes appreciation for natural beauty, revealing electromagnetic phenomena as more elegant, surprising, and creatively powerful than early investigators could have imagined, while simultaneously opening infinite horizons for future discoveries that will undoubtedly challenge current theoretical frameworks through experimental observations requiring new conceptual tools and mathematical techniques. How does it feel to look around your space now and recognize that every photon reaching your eyes represents a small miracle of quantum mechanics, a massless messenger that somehow carries the creative power to build universes while weighing absolutely nothing? Our gentle exploration has revealed light not merely as illumination, but as the fundamental architect of reality, operating through electromagnetic interactions that enable atomic bonding, stellar nucleosynthesis, biological process, and conscious observation itself through mechanisms that transcend classical understanding, while remaining mathematically precise and experimentally verifiable. The photons streaming from your lamp, filtering through windows, or glowing from electronic displays now carry deeper significance as quantum entities exhibiting wave-particle duality, emerging from electromagnetic fields that permeate all spacetime, and participating in virtual exchanges that mediate forces throughout the material world. Each electromagnetic quantum demonstrates the beautiful impossibility of existence itself, where zero-rest mass particles transport finite energy and momentum across cosmic distances, while facilitating pair production processes that convert pure radiation into substantial matter through interactions governed by special relativity and quantum field theory principles. Virtual photons invisibly mediating electromagnetic forces between atoms in your body, furniture, and surroundings operate continuously below detection thresholds, yet produce the stability, coherence, and structural integrity that enables complex chemistry, biological function, and material organization throughout your immediate environment. The strange beauty of quantum mechanical reality emerges through recognizing that apparent emptiness contains dynamic activity where vacuum fluctuations create measurable forces, support spontaneous emission process, and provide the foundation from which all electromagnetic phenomena arise. Through field excitations that follow mathematical laws more elegant than classical physics could have anticipated, wave function collapse, superposition states, quantum entanglement, and measurement effects that initially seemed contradictory now appear as complementary aspects of a deeper quantum reality where observation participates actively in creating observed phenomena rather than simply revealing pre-existing properties through passive detection techniques. Uncertainty principles that once frustrated attempts to achieve complete deterministic control now inspire appreciation for natural creativity and spontaneity, where quantum randomness enables rather than prevents the formation of complex structures through statistical processes that build order from apparent chaos across multiple organizational scales. Thank you for sharing this contemplative journey through photon physics, where scientific precision coexists beautifully with the profound mystery, demonstrating how mathematical frameworks can illuminate natural phenomena while simultaneously revealing the limitations of human comprehension when confronting quantum mechanical principles that operate according to logic fundamentally different from everyday experience. Your patience with complex concepts, willingness to embrace paradox, and openness to reconsidering assumptions about physical reality have enabled this exploration to unfold naturally, without rushing toward premature conclusions that might diminish wonder, rather than enhancing understanding of electromagnetic radiation's central role in cosmic evolution. Continue exploring quantum mysteries through whatever pathways spark your curiosity, whether through additional scientific education, experimental observation of light phenomena, contemplation of philosophical implications, or simply maintaining appreciation for the remarkable universe that quantum mechanics reveals around us every moment through processes that remain as fascinating today as when first discovered by pioneering researchers. The comfort of cosmic mystery provides a gentle resting place where intellectual humility meets scientific wonder, acknowledging that complete understanding may forever remain beyond human reach, while celebrating how partial knowledge opens rather than closes doorways to deeper appreciation of natural beauty operating through mechanisms more subtle and creative than classical intuition could have imagined. Rest peacefully in the knowledge that photons will continue their cosmic work throughout the night, carrying information between distant stars, mediating chemical reactions in your sleeping body, and maintaining the electromagnetic interactions that preserve atomic structure while you dream, demonstrating that the universe operates according to principles far more interesting than simple mechanical processes. Sleep well, knowing that tomorrow will bring new opportunities to observe light phenomena with enhanced understanding, whether through sunrise colors created by atmospheric scattering, rainbow displays resulting from water droplet refraction, or simply the gentle illumination that enables vision through quantum mechanical interactions between electromagnetic radiation and specialized proteins within your eyes. The photon paradox of everything emerging from nothing will continue inspiring scientists, philosophers, and curious individuals who recognize that the most profound questions often lack simple answers, while nonetheless rewarding patient investigation with insights that transform our relationship with natural world and our place within cosmic evolution. Dream gently of massless particles building massive reality through processes that demonstrate how the universe creates beauty, complexity, and consciousness from fundamental principles operating at quantum scales where ordinary language fails, yet mathematical poetry achieves extraordinary precision in describing phenomena that exceed imagination while remaining absolutely real and continuously present throughout every moment of existence.